Not refactoring, not rewriting, but a secret third thing. I'm Ray Myers. Welcome to Craft vs. Cruft. And welcome back. It's been a little while. A couple weeks ago, I was at Craft conference in Budapest with my talk Code Mending in the AI Age. And if you'd like to follow some of my more AI-centric content, I'm going to now be putting that out at this Nopilot channel. Last week's was a response to the notion of the end of programming. But we're back in Craft vs. Cruft channel, where it is the year of formal methods. And so while we will make some passing references to AI, I'm going to let formal methods take the center stage today. But when I was out in Europe, who did I run into? But Emily Bache, perhaps the undisputed queen of code katas, honestly. If you look at this treasure trove, this absolute treasure trove she has up on her GitHub, like kata after kata after kata after kata, and it goes on and on. And a few of these, Trip Service Kata and Gilded Rose, I've done a couple of versions actually. Over here you can see I've got my initial one was a few years back, solving Gilded Rose Kata with no nesting. And a few months ago, I did one with proofs in the language Daphne. So we're going to look at Gilded Rose again, and we're going to use formal methods on it again. But let me point out some deficiencies in the approach I did before with Daphne. Now, Daphne is this really interesting proof-aware language that can compile to a number of industrial languages like C#, Java, Python, Go, and JavaScript. So if you have an application in any of those languages, it's possible to make what's called a verified core that you've written in Daphne and then cross-compiled, and then you go through this kind of weird interface to call it. But nonetheless, you can have hybrid programs, part of which are proven, but yet all of which run in your traditional language in this way. So that's really cool. But in some ways, it's kind of cheating to take the Gilded Rose exercise and then just drop it in another programming language, as many have done to showcase things you can do in that language, because it's a legacy code exercise. So, you know, great. If I'm in Daphne, I can do all this stuff, but my code's not already in Daphne. So this would involve porting it there in order to do that. Second, in order to prove equivalence between my rewritten version and the original, I have to introduce this formal specification. Well, you might say, Ray, I am still just trying to get tests around my legacy code, let alone do I have a formal specification around it. Okay, fair, but you know, formal methods might still be for you. You may not be able to go with full formal specification and verification, but there's also this whole world of formal modeling where you only pick small parts of the problem that you're going to be this rigorous with. We're going to do something different here though. We are still going to attain that level of confidence, but we're not going to need to write a formal specification. Not going to need you to know how all this works, and we're not going to need to move out of our industrial language. We're going to start with the Gilded Rose example in C, and we're going to leave it in C. And I am nonetheless going to prove full functional equivalence between not a refactored version, but a rewritten version. We've been told that was impossible. I'm going to do it in a moment, and I'm going to show you how you can. So I'd like to borrow and expand upon a term that Arlo Bache is fond of using: provable refactorings. These are recipes for changing a code base in certain ways that you can follow either with automation or very deliberately with your hands that will guarantee the code behaves entirely the same as when it started. You will not even fix a bug by accident. He likes to say we need bug for bug compatibility. If we're doing refactoring, the code must behave exactly the same when we're done. If we're going to change its behavior, we're doing a separate thing. Often I'll be using the refactoring tools that JetBrains provides in C# or Java, and using certain ones of those and being aware of their limitations, you are almost invincible with respect to making these small gradual changes without changing the behavior. The term I'm going to introduce here is provable rewrites. A refactoring is used as a contrast to doing an undisciplined rewrite of code where you cannot guarantee the behavior has remained the same. But what if under certain circumstances you could guarantee full functional equivalence on an open-ended rewrite? Would it then be a refactoring? Unclear. Maybe we just need to have a meeting to determine whether or not this is refactoring. This is a gray area, but nonetheless, it is high assurance. And I think it will be very useful to us. To show some recent history of this discussion as it pertains to the AI conversation, Emily's got this great video here. ChatGPT and Copilot are not refactoring tools. And I can add to that unfortunately the AI refactoring menus that JetBrains has recently added in their AI assistant is also not a refactoring tool, confusingly, because JetBrains does have the best refactoring tools, but they have not integrated, last I checked, their AI assistant with their refactoring tools. Emily claims, and I agree, that there is an authoritative definition of what constitutes refactoring and what constitutes a refactoring tool. Those would be the ones set out by Martin Fowler, who literally wrote the book on refactoring based on some earlier academic research and some tools in the Smalltalk community. She points out a 2001 article by Fowler, Crossing Refactoring's Rubicon, where he is celebrating that real refactoring tooling is finally crossing over into the Java world, where it is now in a stronghold. He credits the first commercial tool that supported refactoring, which was Smalltalk's refactoring browser. Amazing thing. And there's kind of a key line here. To go to the full extent into refactoring, you actually have to analyze and manipulate the parse tree of the program. So a refactoring tool certainly isn't a raw text search and replace, and it certainly isn't ChatGPT rewriting your code, which very often produces code that doesn't even compile. Is the disciplined application of rewrite rules that take place at the level of the language's syntax tree. In terms of making confident changes to a legacy code base, it is just a phenomenally useful tool. Now, might you have some good tests that you run, and then you're able to safely just rewrite code? Yes, that's just fine, and you can trust that to the extent you trust your tests. But if you're doing an operation that can be handled by an automatic syntax transformation, then it is almost always safer to do that instead. So with these new AI assistants, I would really love to see them have proper integration with these safe refactoring tools. And those techniques are part of what my talk at Craft was about. I know I promised you a brand new technique. We're getting there. Klee, the symbolic execution engine for the LLVM compiler infrastructure. Now, this was actually introduced in 2008. In this paper, Klee unassisted and automatic generation of high coverage tests for complex systems programs. And they've run this process on the entire GNU core utils. That's the suite of tools that has like ls and find and stuff. You're really bread and butter Unix command line utils. You can give that a read, but very briefly, I'm going to talk to you about what symbolic execution is. It's running an interpreter for all possible inputs of a piece of code. Is that possible? Well, actually, if you've done algebra, you've already reasoned symbolically, right? If you take 5 and add 1, well, you've got 6. But if you just take x and add 1, well, you don't have anything in particular. You have just x plus 1. And then if in the next step you're multiplying it by 2, okay, now you have the quantity x plus 1 times 2, or you have 2x plus 2, but you don't know specifically what you have. You just have to carry it on, right? So you can imagine running an interpreter for a programming language, or in this case, for the LLVM intermediate representation, which is part of what some C compilers use in between C and going to binary. You can go through all these steps, taking symbolic inputs and saying, okay, based on all I know about this variable, which may be very little besides its type, or it may be constrained to some range or something. Now what do I have after this operation's been done? But there are branches, right? There are if statements. So then we just make a tree of possible execution states we could be in. We could be over here with values in these ranges, or we could be over here with values in these ranges. You can picture how this could work. It's not obvious that it could ever be efficient. And sometimes it's not, because they have something called path explosion, where there's just too many possible paths and it can't fit it all in memory. But amazingly, there are useful situations in which we can actually do this. And there are backend tools like Z3, which is an SMT solver, a type of SAT solver. You might see it in Sudoku solvers and things. That ends up helping collapse the search space and make this a little more tractable. All right, enough talk. So I'm going to take the Gilded Rose exercise from the Refactoring Kata /C directory, and I'm going to put it in my own repo, which I'm going to link, that just has a few things added, but actually nothing changed from this original code. We're going to operate on this vanilla C code. I'm not going to explain the full problem statement for the Gilded Rose Kata here. You can go to the links or you can watch another video for that. But this is just a time-honored piece of practice code because of how well it reflects what happens when requirements are just sort of slowly added over time, and then you just get these ifs within ifs and this coupled stuff, and it becomes hard to add a new feature correctly. Now I'm going to build this fresh, and there are some approval tests here that I can run with make test, and it will capture the output to a text file, and it will compare it against what's called the golden file, right? The one which has the legacy behavior in it. So as long as we match that output, we're going to be okay. Typically, we would think. And to show you how this would look, it shows the quality and sell-in date of these items tracked over time from a start state, and this will catch most bugs in it. These are, you know, pretty decent tests for this situation. But I didn't promise you I was going to check the fidelity of a rewrite with tests. I promised you that I had some formal methods magic on how to do it. So what I'm going to do is I'm going to take this and I'm going to paste it into a reference copy. This update quality function has just been renamed update quality reference. And this is my reference implementation. My legacy, the one that's in prod, is the implementation that we're going to keep the same, and then we're going to modify this other one, and we're going to make sure they return the same value without even actually running the code. How are we going to do that? We're going to use this Klee tool, and I'm setting up a harness over here. It wouldn't be part of the production executable. It would just be used to run this check. I'm going to start at the end here. I'm calling update quality on an item that has been set up. Okay, this should look normal. I'm also calling another copy of that item with update quality, the reference implementation, and I'm asserting that they've produced the same result. Okay, that makes sense. That sounds like something you might do in a unit test. This is anything but a unit test. Let's read it from the beginning. And just ignore the undefined symbol warning in the editor here. It's going to be built in a way the editor doesn't understand. We're declaring these variables, and then we're telling Klee, make these symbolic variables. So it means as this is simulating the execution, these will take every value they possibly could at once, right? So sell in quality, and I'm not actually going to make it symbolic over the name of the item because there are only a few item names that are actually going to occur. So I'm going to declare this int called name choice. And I'm going to use something called assume, which is like an assert, but instead of blowing up if it gets violated, it just constrains the search space. So I'm going to assume name choice is greater than or equal to 0 and less than or equal to 2. So these are the items that we're going to run for. We haven't added the extra one. All right, so then we build the one we're going to pass into the reference implementation, item ref, and then we build item, which we're going to pass into the main implementation. We're going to call them both and do those asserts. Now, when Klee gets to an assert, what's going to happen? If that assert is ever violated, it's going to point that out. If it can ever be violated in the entire space of values it's been allowed to contemplate. Now, if you try to actually install Klee, as is the case with a lot of these verification tools, it's quite a lot of requirements on your system. So they recommend running Klee in Docker. I've built the image from their Docker file. You can also just pull it. And having done that, yeah, we've got a little Docker shell. So we have Klee on the path. Excellent. And I've mounted a little app folder here that has the repo that we're in. So now if I do make Klee, all right? Okay, so it's going to build it one time. It's going to build it in kind of a special way. There's a warning, but no errors. So those assertions can never get violated. Great. And that's what we expect because we haven't modified the program yet. So we could try a rewrite, but first I want to show you this catching a bug, right? So let's just look at a subtle thing. Like what if this were less than or equal to instead of less than, as it should be? So I've broken it. Will the symbolic executor catch that? Boom! Assertion failure on quality. And we can run a special other command that would tell us the symbolic values of those variables coming in that actually reproduce that, and we could get a test out of it. That's one thing symbolic execution can be used for, is actually automatically generating test cases. But for our purposes today, we're going to see this as binary. It either was equivalent or it's not. So something's gone wrong, and I need to roll back whatever I was doing with that rewrite. But, well, we already had tests. I mean, would those have caught this issue? Quite possibly. So if I just run make test on that, yeah, it does indeed find the error that way as well. So we haven't gained anything from those tests that we already had, assuming you have tests that are that good. You might not. Can I introduce a bug that this wouldn't find? Let's roll this back, get back to green. All right, success. But looking at my golden file, right, what's the range this operates in? How large does the cell and date ever get? What if we introduced a bug that was only active when the cell and date was over 100? I know that sounds kind of contrived for the purposes of this, but we've all seen edge cases that were that surprising and bugs that were introduced, right? Let's say if cellin is less than 100, do what we were doing before, but otherwise don't actually decrease the cell and date for sulfurous. Now will our tests catch it? No, the approval tests have approved. We're fine. We can ship to production. We won't notice it till the user hits it. All right, well, formal methods, you're my only hope. Can Klee catch it? All right, building it again. We have an issue in cellin. So we have to back out that change because there is a permutation somewhere, and that will cause a break in behavior. All right. Now we're back to green. I've just been poking at this now, but what we want to do is just completely rewrite it, right? So let's do something that, if maintaining behavior were really critical, would be an absolutely foolhardy and disastrous thing to do, huh? Let's let ChatGPT rewrite this code. And I'm just going to live dangerously here. I'm going to use 3.5. I'm going to use the bad model here. Say, make this better. Give it this code. All right. And I should point out here that Gilded Rose is all over the internet, surely in the training set. Whatever happens here will not be a representation of ChatGPT's code rewriting ability. It would reflect training set contamination. This isn't a proper demo of AI capabilities. It's about the validation method. All right, so okay, honestly, that's not much better. I'm going to give it a strategy here. Make this more maintainable by extracting methods for each item type to handle their logic separately. That is a way that I think will make solving the exercise by adding a new item type a lot simpler. All right, it hasn't completely followed the instructions, so some of the logic is still in here, but we can paste that in. All right, you notice that is technically already broken because there are no prototypes for these methods before they're used, but that's okay. I can just plop the usage below it and it'll make up for that. So let's ask Klee, is this identical? No, this is not identical. We've broken the behavior in some subtle way. And if we want, we can investigate and see where it went wrong and fix it, but really we got this for near free, right? We could just keep mashing the button until it were right. Or better yet, let's switch to the better model and see if it has any better luck, shall we? So I'm going to send it just the same prompt. This time it's trying to define the struct. We've already got that, so let's not do that. All right, update item. This is how I wanted it to look, right? I wanted to just call out to those. And it's even extracting update quality into a loop. So for Omni is behaving much better. So let's copy that out there. Even put them in an order where it would work, so that's nice. All right, And hey, it behaves identically. So we have a winner. So now we're actually solving the original exercise, right? It's just to, without changing the behavior of the others, introduce the conjured item, which behaves as a normal item, but degrades in quality twice as fast. Like, okay, so we just copy update common, call it update conjured, and subtract 2 quality every day instead of 1, and an extra if block there. Now, not perfect code if you like the object-oriented solution, but hey, we are in C after all. So what's just happened here? We effectively mashed a free auto rewrite button for a small swath of code, and then had a completely reliable check that we weren't modifying the legacy code behavior. In fact, we never even ran the code, and we could already be sure. We haven't even run it. We haven't even run the test, and I'm already claiming that it is behaving identically. So should we run the test? Sure. Okay, yeah, of course the test passed because the symbolic execution showed that they were identical. Now, I don't claim that the tooling allows us to use this technique on all code ever, but I think by showing you unmodified C code that it worked on, and especially that combined with the Klee paper in which they ran it over all of core utils, shows that this does work in a very useful set of circumstances. So just as the refactoring practitioners branch out into fuzzing and into mutation testing, I think it's time to get into formal methods too, and maybe even provable rewrites. I can't wait to try more stuff along these lines. Hope you enjoyed. Leave a comment, let me know what you think. And as Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be undone. Thank you.